Again, last night at the York Code Dojo, we ran Minesweeper as a session, and obviously different groups came up with different methods of solving it, which is always quite interesting. There's a lot of talk around whether we could solve it using brute force or probability, so I thought we could maybe have a quick look at those today. So the idea behind brute force is to try every single combination until we end up with the answer. So really we have to build a tree of solutions. So if we think about it, we from the first empty cell we've got two choices. We can either populate it with a mine or say it's empty. So we have two possible solutions from that first cell. And then when we get to the second cell, we've got the same two possible decisions to make. We can either give it a mine or again it could be empty. So then our tree then begins to look like. And if instead of saying we put a mine in the original cell, we put empty in the original cell, then again we have the two possibilities. And we keep repeating this tree sort of structure until we get right to the end of the board. Oops. And so on. So if we get to the end of the tree, so there'll be one node for every empty cell on the board, and we successfully get to there, we know we found our solution. If, however, we get to a point where the board's not valid, so not valid, for example, this cell here has ended up with two neighbours which contain mines, so it's not valid, we have to backtrack up that node and then try the other route. So in this case, maybe we'd put a mine in there, we know that's not right, so we undo that mine, we say it's empty, we try that. If that also doesn't work, we backtrack here, we've tried both our solutions, so then we have to undo the mine we put in that cell, which might be that one for example, and then try that one empty, and so on. Until eventually we should get the answer. I think the idea behind probability was instead of walking this entire tree, the idea was to make decisions based on which of the nodes was the most likely to contain the mine. So anyway, for this video we're just going to look at brute forcing it, and then maybe we can look at using probability later on. So the basic idea is we're going to add a new button to this form called brute force. We click it and then it's going to build and walk that tree as we've just discussed. So let's add the button to start with. Be consistent. And we need to set its location because otherwise it's on top of the other button. So so we need to move it along. So I'll just put it there for the moment. Right, that's that button added. Right, so we're going to add a new method to our game object, which will be, I don't know, let's just call it brute force. And then, so that's going to solve it, and then we need to draw the board. Yep. So we're not going to get any diagnostics information back, we're just going to get back the completed board, and then so we solve it all, we clear the display, and then we redraw it. So we can create our method now. Okay, so this is going to be our recursive method for walking down the tree. So This method is going to return true once it finds a valid solution, and it's going to return false if its solution isn't valid. So, as with all recursion, you have to start off about thinking what's your exit point going to be, how are you going to stop recursing. Well, in this case, it's going to be if we've got no more empty cells, then we know we found the solution. So, first of all, we need to find the next empty cell. Just stop that out for a second. So that's going to return a cell location. Now, it's possible that there are no more empty cells, and because cell location is a struct, we can't return null, but I've actually already added to it a couple of alpha methods, one called not used and is unused. So we can represent a missing or non-existent cell as being -1. We can use that again. So if that's unused, so there's no more empty cells, the board's valid, so therefore that must be our solution, so we can return true. Okay, so otherwise we now have an empty cell, so we want to try setting that to be a mine. So after we've played a move, we now need to see if the board's valid. So we've made our move, so we've set that to be a mine. Use text to be easier. We've set that to be a mine. So the next thing is say, are we in a valid case? If we're not in a valid case, we need to undo that. But we are in a valid case, we can continue onwards. So we can use our game validator class we've already got. That returns an object with results. So if it is valid, that's good. So then we can then call our function again. So if that returns a valid result, then so that returns a valid result from down there. That means it's successfully got to the end of the tree and we found our solution. If it doesn't return a valid result, then we know the mine wasn't the right answer, so we need to try an empty cell instead. So it's the same thing, and if that doesn't work, then we're at this case where we've tried that, neither of those were okay, so we need to undo where we were and go down that route instead. So we need to put that back to unknown to undo what we've just done, and return false because this wasn't the answer. Okay, so the next thing is we need to find our next empty cell. So if we just we look at each cell in turn. If we get to the end, there isn't any more empty cells. Otherwise, oh, yeah. Actually, I'm going to call that unknown cell. That's a better word for it. Okay, let's see if that works. And it does. And it's quite fast as well. So what I'll do is I'll commit this code to GitHub, and then maybe in another video we'll look at using probability to take a more efficient route down that tree. Thank you.